Today we're going to talk about the information from Chapter 11, specifically the first 4 sections. And we are talking about fundamental counting principle, permutations, combinations, and the fundamentals of probability. And we use this to understand data, understand ways to make selections, and understand what's going on. If we had, let's just kind of jump right into it. If I had number of shirts and a number of pairs of pants, I could create quite a few outfits. Maybe if I had a black shirt, a red shirt, let's say a white shirt, and blue. I probably have lots of blue shirts. And with pants, let's say I have black pants and I have khaki pants. So I've got 2 pairs of pants, I've got 4 shirts. How many outfits could I make? Now we've got a couple of ways we could look at this. We could draw a little figure, say black shirt with black pants, or a black shirt with khaki pants. Maybe I take the red shirt with black pants, or the red shirt with khaki pants. And I could do that for each of these shirts. And we can get the total number of outfits. So it looks like 2, 4, 6, 8 total outfits with 4 shirts and 2 pairs of pants. Now, if we add shoes to that, that looks like a clown shoe, but that's okay, we'll count it. And maybe I have black shoes and let's see, I need something that doesn't start with B, maybe green shoes. I don't really, but we'll pretend just for the sake of things. And I can go ahead and continue this figure like we had before. So we could have black shirt, black pants, and black shoes, or black shirt, black pants, and green shoes. Black shirt, khaki pants, black shoes, black shirt, khaki pants, green shoes. So we could continue that, and you would see that I would have twice as many options as we had before. It would be 2 times the number we had before for a total of 16 outfits. Well, this follows with what is called the fundamental counting principle. And the fundamental counting principle says if I'm trying to choose one item from a group of M items, and maybe we'll call the shirt the M items, and a second item from a group of N items, and we'll call that maybe the pants, then the total number of item choices is M times N, and we saw that before. The number of shirts times the number of pants gave us 8 total outfits. And then when we had shirt and pants and shoes, we could multiply those together. 4 times 2 is 8, times 2 is 16. And so graphically, we came up with 16 items, but we could also use the fundamental counting principle and get to that same 16 items. You just multiply the number of options in each group together, and that gives you the total number of options. If we look at a problem like this, it might help us figure that sort of thing out. Next semester, it says we're planning to take 3 courses. We've got math, we've got English, and we've got humanities. And so we'll take those classes there, and it says we've got certain time blocks, of course. You've registered for classes, you know how it works. It talks about highly recommended professors. It says there are 8 sections of math. It says there are 5 sections of English, and there are 4 humanities sections that are all suitable, and they could all be used at any given time. So if there are no scheduling conflicts among all of those sections, how many different 3-course schedules can you get? fundamental counting principle says I just multiply the number of items in each section together. Now, a fast way to do this might be 5 times 4, which is 20, and 20 times 8 isn't too bad because 8 times 2 is 16, and then we had the other 0 on the end. So we had 160 different options. We could also have done 8 times 5 first, which is 40 times 4. 4 times 4 is 16, and then we have the 0 on the end. Or we could, of course, pull up a calculator and do 8 times 5 times 4 and get the same result. So a number of different ways we can come up with that 160, but the concept is the same. You multiply the number of available options in each category by the number of available items in other categories, and it will give you your total available options. If we look at another problem, we could see something similar here. So we're talking now about a car manufacturer and talking about three-wheel cars, it looks like. Suppose you could order such a car with a choice of 9 colors. So colors would be 9. I'll keep it red. With or without air conditioning. So for the AC, we've got with or without, that's 2 options. And then electric or gas powered. So power has 2 options. With or without an onboard computer. So the computer had 2 options, with or without. In how many ways can we order that car? Well, let's just multiply all of those together. 2 times 2 is 4, times 2 is 8, and 9 times 8 is 72. So we have 72 different ways we could order this particular car. You really just have to pay careful attention to what's written in the text and how many different categories we have there to work on. But once you've got that figured out, just multiply those numbers together. Here we're taking a multiple choice test that has 10 questions. Each of the questions has 4 answers. If we select one of the 4 choices for each question, leave nothing blank, in how many ways can we answer the question? So it's tempting to do, well, I've got 10 questions, I've got 4 answers, 10 times 4 is 40, but that's not quite going to work out for us because those aren't separate categories. One thing is actually defining another. So maybe what I'll do is I'll write out 10 lines to represent the 10 questions, and each one has 4 choices. And now you can see that it is not quite as simple as 4 times 10. We actually have 10 4s we are going to multiply together. And so what we will do is 4 times 4 times 4, 10 of those. And you know, it's a little faster to use exponents. That's the same thing as 4 raised to the 10th power. That's a lot faster to type into the calculator. So I could take 4 and raise it to the 10th power, and that gives me 1,048,576. There are that many different ways you could answer a 10-question quiz. Probably worth studying then, because you only have a 1 in a 1 million chance of getting them all right if you're only guessing. So studying seems like the best approach to figure out how best to solve that. All right, now let's look at permutations. This jumps into section 11.2. And it starts by saying, we need to arrange 7 of our favorite books along a small shelf. So let's take a look. Say we've got this shelf, and we're putting 7 books in there, so it's as if there are 7 different slots we could fill. See, that's 6, there's 7. And so if I were aligning these, and order kind of made a difference to me, how many different ways can I rearrange this? So let's think about this for a minute. If I had the 7 books sitting here on the floor next to me and I was putting them on the shelf, how many different books do I have available for the first slot? Well, that would be all 7. But once I place the 1, how many do I have available for the second slot? Now I only have 6 available. Now that I've placed those 2, how many do I have available for the third slot? 5. And you can see the pattern here. It will steadily just decrease until I only have 1 book left. And of course, that would go on the end. The fundamental counting principle says that now I multiply all of those together. And when I do that, now this one isn't as simple as some number raised to a power. I have to multiply all of those. So let's go to our calculator here. 7 times 6 times 5 times 4 times 3 times 2 times 1. That's a lot of writing just to get a simple number of 5,040. But that tells us how many options we have available to us. Well, luckily, there is another way to write that so it's faster, and it's called a factorial. And a factorial, which is denoted by an exclamation point, is the same thing as multiplying all of those integers together from the number we're looking at down to 1. So, for example, 7 factorial equals 7 times 6 times 5 times 4 times 3 times 2 times 1. So that whole product we got together, the 5,040, we can write much simpler as just 7 exclamation point. And I'm going to show you on this calculator how to find that. This is common for lots of calculators. Notice this PRB button right up here. In this calculator, it's up here near the top. And under PRB, it gives me 3 options: NPR, NCR, and the exclamation point. And so I can either hit the down arrow twice to get to the exclamation point, or when I come in here, I could just hit the 3, and that would give me that exclamation. So let me go ahead, I'm going to clear that and make sure I've got 7, and then I'll hit PRB, and I'll hit 3 because I want the third option. There's my 7 factorial. I hit enter, and there's my 5,040, just like we got before. So that's a much faster way to calculate some number multiplied by each consecutive smaller integer down to 1. And so we could have done that when we were calculating how many different ways we could arrange these 7 books along this small shelf. And we will use factorials several times here. Let's take a look at an idea that kind of expands from that. If I have 13 boys playing baseball, and I want to create a lineup, and I think about how many players are on a field at a time, and that's 9. There are only 9 baseball positions. And so I need to pick those 13 boys in such a way that 9 of them are prepared to play. So let's take a look at that idea. I've got 13 factorial different ways to arrange 13 boys. I'm going to say on a small shelf, but the reality is I'm just lining them up. But I can only use 9 of them. So somehow I need to not think about the other 4. If I were to divide this by 4 times 3 times 2 times 1, then I could see that these numbers on the end would cancel, and that would take care of the fact that I'm really only looking at 9 players, because I only have 9 numbers available. So it would be useful to me if I took that 13 factorial and then I somehow had to get 4 factorial. in the denominator. And notice that if I take that 13 minus 9, I get 4. And it will always work out that way. So I can take the number of things available to me to pick and subtract from that the number of positions I'm filling. And that will give me the perfect number of combinations, I should say permutations, since that's what they are, that work to fill, in this case, 9 slots with 13 different boys. And we call that, like I said, a permutation. There is a notation for that, and that is NPR. NPR, not just National Public Radio, is a permutation of n things taken r at a time. So that's what that means. So we could say, now we could plug all that into our calculator, but now that we know a faster way, we want 13 things, a permutation of 13 things taken 9 at a time. And you saw that in the calculator here under the probability. Let me go ahead and clear this. We'll take 13 things. I'll hit the probability button and I want NPR. So I'll just hit the 1. We were taking them 9 at a time. Now when I hit enter, I still get a really big number, but it's not as big as 13 factorial. Let me see if I can do that and keep it, both of those on the screen. See, that's 13 factorial, and we definitely had fewer than that because we weren't filling all 13 slots. But there are that many different ways, 259,459,200 ways to order those 13 boys to fill the 9 slots. That's a permutation. We'll have easier or smaller numbers, but that's the fast way to do it. Now, remember what I said, that 13 NPR 9 gives us that number. We could, if we wanted, set up the fraction where we had 13 factorial, and we're going to divide that by 13 minus 9 factorial, and you'll see it gives us the exact same number. So we could do it kind of longhand with all the factorials, or we can do it shorthand, just the NPR. Now, some calculators have an NPR button. It's often a second or one of the words written above a button, so you have to hit the second or shift key to get to it. But others have a PRB button. With some calculators, you need to hit the math menu, the math button, and it opens a menu, and you'll have a PROB menu about 3 spaces over to the right. And if you use your arrow keys to move over to that, you'll see the exclamation point, the NPR or the NCR. So get used to how your calculator does it. But once you do, these calculations are so fast. It's unbelievable how fast they are. This homework is way easier than what we've been dealing with chapter 8. So let's take a look at this problem. We've got 19 friends who've decided to form an internet marketing consulting. We need to choose 3 officers, a CEO, an operating manager, and a treasurer. How many ways can we fill that? Well, we've got 19 things, and we are choosing 3 of them. So 19P3 or 19 NPR 3, and that gives me 5,814. So there are 5,814 ways we could pick 3 people to fill those slots. And that's kind of a nice, quick, easy way to see what the number of options are. That's a lot of options. And odds are good you're not going to go through every consideration there and figure out which one would actually work best for your company. But it's nice to know that we have that way to calculate how many there are. Here's an interesting question in my mind. we've got how many different ways can we rearrange the letters of the word Mississippi. Now, I'd like to mention something now, kind of about that. If I had the word, I don't know, let's see, trying to think of a good dad. Dad is a good word. Only 3 letters. I'll rearrange those. Maybe I start with A, so I've got ADD. Maybe I start with D, so DAD. Maybe I start with the other D, DAD. Well, those two are exactly the same, right? You can't tell which D I started with. And so we need to account for that. We need to remove those duplicates. So what I'm going to do is I'm going to write out the different letters that we're using in this word. I have 1 M, I have 4 I's, I have 4 S's, and I have 2 P's. So I need to somehow account for that. Now that's 11 total letters. 11 factorial would give me what I need, except once again, I need to account for those duplicates. So what I do is I divide by the number of items that are duplicated. So because I had 4 I's, I need a 4 factorial in the denominator. Because I had 4 S's, I need a 4 factorial for the S's. And I need a 2 factorial for the P's. Now I just wrote them like this, but you may need to put multiplication between those for your calculator. So let's go ahead and clear this out. And I'm going to go ahead and use the fraction button because I like that. So I need an 11, not 111. I need 11 factorial in the numerator. And then in the denominator, I'm going to try it without the multiplication, see if it works. 4 factorial, 4 factorial, 2 factorial, just to see if it works on this calculator. I don't know if it does or not. Oh, 34,650. So there are 34,650 different ways to rearrange the letters in the word Mississippi so that we take account the fact that sometimes you can't tell the difference if that's the first S at the start or the second or the third or the fourth. Either way, it's going to work for me. So if we have duplicates, we have to take those into account, and we will be dividing by the number of duplicates factorial and however many of those there are. So that'll clear up when we have duplicates. Because one of the key factors for a permutation to work is we will not have any number repeated. Because we had letters repeated here, we had to divide by those. But for a permutation to work, we'd have no duplicates. And an interesting thing about that is order also has to matter. Order mattered for that last problem, where we had the 3 officers, because the person filling a CEO position doesn't do the same kind of work as somebody who's an operating manager. You want very particular people in there doing those jobs. So we're not just going to pick 3 people and, okay, you guys pick which one you want. We're going to put the best people in the best position for them. So order clearly matters. Well, sometimes order doesn't matter. Sometimes it's okay either way. For example, we had A, B, C, D, and we needed to rearrange those 3 of those letters. Well, I could have A, B, C. I could then swap the last 2. I could maybe start with B and then swap the last 2. Or I could start with C and swap the last 2. Maybe I don't use B. I use ACD. So I've got ACD and swap the last 2. Or I start with C and swap the last 2. Or I start with D and swap the last 2. So now we've considered every consideration with A, B, and C, everyone with ACD. maybe we use, let's see, how about ABD? We haven't done that one. ABD and swap the last two. Maybe we start with B and swap the last two. Or maybe we start with D and swap the last two. So we've covered those. Maybe we don't use A. Maybe we just use BCD. We could swap the last two. We could start with D, swap the last two. We could start with C, or swap the last two. So you can see we've got 6 in each column for a total of 24 different options, which works great. And we can do that 4, P, 3, and we would get 24. Maybe we should take a look and make sure that's the case. Or NPR 3 gives us 24 options. Well, if I look at these in this column, if order didn't matter, then ABC is the same as ACB. I'm using the same 3 letters. And if order doesn't matter, then this whole column is basically one option, as is the next column. And so if order doesn't matter, we have to find some way to get this 24 be reduced down to 4. Well, remember, the permutation of 4 things taken 3 at a time is 4 factorial over 4 minus 3 factorial. Well, somehow we need to divide that by 6. And as it turns out, 3 factorial, which is 3 times 2 times 1, is 6. So notice what we've done here. We've taken n factorial, we've divided by n minus r factorial, and then r factorial. And it turns out that is a combination. So a combination is another way to arrange things when we're taking portions of a group. A permutation was our first way. And what was the big difference? Whether order mattered or not. So order does not matter for a combination. That was key, and that was why we divided by 6, because ABC equals ACB if order does not matter. But order does matter for a permutation. And so if you're looking for a CEO of your company and a secretary and a vice president, order matters, and so you would use a permutation. Order does not matter. Like, I just need 3 people to sit on a committee. They're all equals. It doesn't matter what order they're picked, then I would use a combination. If I'm receiving cards dealt to me, it doesn't matter whether I receive 3 3s and then 2 2s. That's a full house, or I get 2 2s and 3 3s after that. It's a full house. I'm dealt one at a time. As long as I have the same 5 cards, it doesn't matter what order they came in. That would be a combination. So that's the difference between the two. If order does not matter, it's a combination. If order does matter, it's a permutation. And so we've got the NPR and we've got the NCR, or a permutation and a combination. NPR is the permutation, NCR is the combination. And again, on your calculator, it's located very closely to the factorial. You saw in the calculator I keep bringing up that those are under the PRB menu. If you have a PRB button, or you go to a prob menu, those will be there. If your factorial was on its own button, then you'll have to look for another button that has NPR or NCR associated with it. But that will allow you to calculate those, again, fairly quickly. Let's take a look at this problem. Here we need a 3-person committee to study ways of improving transportation. How many committees could be formed from 8 people? So we've got 8 people, and we're making a committee of 3. Notice it doesn't say that their jobs are any different, so that would be a combination. So I'm going to go to my calculator, and I'm going to take 8 things, and I will do NCR now, 3 at a time, and that gives me 56 different ways I could pick a committee of 3 out of this group of 8 people. If I had done NPR, the number would be much bigger. Let's try that. 8 NPR, 3, and I get 336 ways. Notice that with NCR, we've divided by R factorial again in the denominator, whereas NPR didn't have that extra R factorial. So the NCR numbers will always be smaller than the NPR. Just watch for that. Some of the homework will ask you, do you use a permutation or a combination? And it all comes down to whether or not order matters. Let's take a look at another problem. Oh, here in poker, again, we're dealt 5 cards. The order in which they're received does not matter. It says how many different 5-card poker hands are possible. Got 52 cards. We're choosing them 5 at a time. Order does not matter, so it's a combination. So I'll take 52. I'll go to my probability menu and choose NCR. I'm getting them 5 at a time. And that gives me a whole bunch. 2,598,960. 2,598,960 different ways to get 5 cards. That's why poker can be so challenging. You've got so many hands available to you at the start when the cards are first dealt to you. Let's look at another problem here. In the US Senate in 2017, there were 46 Democrats, 52 Republicans, and 2 independents. There are 100 senators in our US Senate, 2 from every state. So those I'll add to 100. So we've got 46 Democrats, we've got 52 Republicans, and we've got 2 independents. The question is, how many distinct 5-person committees can be formed if each committee must have 2 Democrats and 3 Republicans? So I look at this and I think, well, we kind of have a couple of different problems here. I need 2 Democrats, I need 3 Republicans, so 0 independents. But notice that even the way I wrote it here, we have 46 Democrats, I need to pick 2 of them. That sounds like a combination. So let's go ahead and do that. 46 senators, chosen 2 at a time, gives me 1,035 different ways to choose that many Democratic senators to sit on this committee. I've got 52 Republicans, and I need to choose 3 of those. Again, order would not matter because they don't have different jobs. So 52 senators chosen 3 at a time gives me 22,100. So I have that many potential ways to select Republicans. I have 1,035 different ways to select Democrats. This feels an awful lot like the first problems we talked about in this video, where I had so many options of shirts and so many options of pants, and I just multiplied those numbers together. So let's do that here. We will take 1035 and multiply that by 22,100. Now notice I've got 22,100 as my last answer. It will remember that. So I can just hit times, because it remembers my last answer, 1035. Or I could have typed the whole thing in from scratch. And I get, wow, big number, 22,873,500. A lot of different ways to choose senators to sit on a 5-person committee with those restrictions in place. So this is a combination, see what I did there? Combination of combinations, and the fundamental counting principle. So watch for that. You may have that show up from time to time, but it works really well. So that ends section 11.3, which was combination. Now let's take a look at probability, which is 11.4. We have two different types of probability that we will look at. The two types are theoretical and empirical. So, well, it helps if you type it correctly. So we've got theoretical. So clearly it's a theory. And we've got empirical. We have a definition of probability. This is theoretical. Notice we take the number of outcomes in an event and divide it by the number of possible outcomes. So theoretical is just possible. It's not guaranteed. It's what we expect based on the numbers. So number of event outcomes, how many options would give us what we're looking for divided by number of possibles. I think seeing a sample problem will really help with that. Anytime you see the word empirical, it means it's based on real numbers. And so those calculations will appear slightly different. We will be using real data for empirical probability. But theoretical, it's just kind of what is possible, what might happen. And let's see a few problems and you'll see how easy this really is. Here's a problem. A die is rolled once. Remember that you've probably seen dice. They're just a cube and they've got numbers on the sides. Sometimes they're written as numbers, sometimes they're dots. But since there are 6 sides to a cube, there are 6 numbers written out there. So find the probability, it says, of rolling a 3. This will be theoretical. So we'll take the number of event outcomes. How many 3s are on a die? Well, there's 1 of those. Out of the total possible, there are 6 possible numbers. So it's 1/6. That's how you do that. With B, what are the odds of getting an even number? Well, how many evens are there? There's 2, 4, and 6. So we've got 3 possible outcomes that fit what we're looking at out of 6 total possible numbers we could get. Simplify that down to 1 out of 2. So if I roll the dice, I've got a 50-50 chance of getting an even number. Maybe we look at a number less than 5. How many numbers are less than 5? We've got 1, 2, 3, and 4. So that's 4 possible outcomes out of 6 possible numbers. Simplify that down to 2 out of 3. You've got a 2 out of 3 chance of rolling a number less than 5. Let's take a look at a number less than 10. Well, how many numbers on the die are less than 10? 6 of them. Out of how many total numbers possible? 6. So you've got a 100% chance that you will roll a number less than 10. And for E, a number greater than 6, how many numbers are greater than 6 on a die? 0. Out of how many possible numbers? 6. So you have a 0% chance of rolling a number greater than 6 on the die. So it's pretty straightforward like that. You just look at how many numbers fit what you're looking at and divide it by the total possible numbers. And we do have a number of questions that deal with cards. And so I want to make sure you're aware of how cards are organized. It's a 52 card deck. It's organized into suits. And those suits are hearts, clubs, diamonds, and spades. Oh, I should have put a black line under clubs and a red line under diamonds because hearts are red and diamonds are red. Spades are black, always, and clubs are black. The numbers on the cards go from ace, which is like a 1, all the way up to 10. And then after 10, we've got a J, a Q, and a K that stand for jacks, queens, and kings. And so there are 13 cards in each suit. And when 13 times 4 is your 52. This means that there are 26 red cards and 26 black cards. But that's a standard deck of cards. And you will have some questions that'll ask you about that. For example, here's one. Suppose we're dealt one card from the standard deck. What's the probability of being dealt a king? Well, there are 4 kings, one in each suit, out of a total of 52. And that would simplify down to 1 out of 13. So you've got a 1 in 13 chance of being dealt a king. How about a heart? There are 13 hearts out of 52 total cards, which simplifies to 1/4. How about the king of hearts? There is only one of those out of 52 cards. So your odds of getting the king of hearts are much lower than the odds of getting any king or a heart itself. Once again, the probability comes out fairly quickly. Just divide the number of potentials that fit exactly what you're looking at, divided by the total possible number of items that we're also looking at. Another theoretical possibility or probability would be genetics. Generally speaking, we've got 2, I'll say, genes that give us certain traits. Some of those genes are dominant and some are recessive. If you have a dominant gene, that will be shown on your phenotype or the way you look. If you have the recessive gene, then you will carry that with you. If you have both a dominant and recessive, the dominant will be shown. And you'll carry the recessive, but it won't be shown. If you have 2 recessives, then that recessive trait will come out. One example is a dominant trait is brown eyes. And a recessive trait would be blue or green eyes. That's why there are more brown-eyed people in the world than blue or green-eyed people. But we will often denote those with a couple of letters. Capital C would be a dominant and lower c would be a recessive. And so if we had somebody with 2 dominant genes marry somebody with a dominant and a recessive, we could create a little table here to understand what their offspring might look like. We will take the column title and write that in. And then we'll take the row value and write that in next to it. And we can see that these 2 both carry on both dominant traits. These 2 have it 1 dominant and 1 recessive. So they will all have the dominant trait, but 2 of them now have the recessive trait to potentially carry on. If you have 2 people who are aligned like that with 1 dominant and 1 recessive trait, that will change your square here. So again, take that column down and now take this column down and then take the row across. We can see that these 3 all have the dominant trait. So they would all carry forward, say, those brown eyes. But this one down in the corner has 2 recessive genes and would therefore have the recessive trait, the blue or green eyes. So while both parents might have brown eyes, one child might carry blue or green eyes because both parents had the recessive gene and they passed those on. Now that's no guarantee that if those parents had 4 kids, one of them would have green eyes. All it says is each child has a 1 in 4 chance of getting both recessive genes and would therefore have green eyes. It's possible that in the real world, all 4 kids got the recessive genes and had blue or green eyes. Doesn't happen very often, but there's definitely a possibility. So you could use that idea to breed new versions of a plant, for example. So you take one parent plant and another parent plant and you mix their genes, there's a chance the offspring would have a characteristic that you're hoping that it would. Now let's look at an empirical probability problem, and you'll see what we were talking about there. So I'm going to enlarge this just a bit so it's easier to see. These are real data. These are the marital status of the US population age 15 or older in 2015. And they might ask us questions like, what is the percentage of divorced people? If we were to pick one person out of this group of people, notice it says up here, this is in millions. So it's 254 million people that it's looking at. If I were to pick one person randomly, what are the odds that I would pick a divorced individual? So notice what we have here. Across this row, those are the males. And the total number of males is 123 million. Across this row are the females, and the total number of females is 131 million. So the right-hand column gives me totals, but notice the bottom row gives me totals. In this column, we've got married individuals for a total of 133 million. This column is never married with a total of 81 million. These are the divorced individuals with a total of 26 million. So that's kind of what we're looking at. Now we want an individual who is divorced. We haven't said anything about their gender, so we'll just use the total divorced, and we'll divide it by the total number available to look at. So 26 divided by 254, and hopefully this calculator will give me an answer that's a fraction, because that's what they want to see. It's like, there we go. This one has a little button with arrows that lets me go from a decimal to a fraction. It gives me the simplified fraction. So it's 13 over 127, and we should always simplify these. 13 out of 127, 13 million out of 127 million, or 13 out of 127. Those are the odds of picking somebody who's divorced. How about a female? Yeah, what are the odds that that person would be female? Well, the total number of females is 131. Out of the total number of people, 254. So 131 out of 254. I don't know that that simplifies very much. Nope. So that is the odds of picking a female randomly. How about a widowed man? So we've got widowed as a column. How many males were widowed? 3. Out of how many total people do we have to pick? 254. And that would be as simple as it gets. Quick check, kind of a fun little fact. If we add all of those digits together, and if that sum is divisible by 3, then so is the whole number. 2 plus 5 is 7, plus 4 is 11. 11 is not divisible by 3. Therefore, 254 isn't divisible by 3. Just a little trick there. So that would be the percent of widowed men, the odds of getting a widowed man when we pick somebody randomly from this group. So that's how we would do our empirical probabilities. You'll have a table, you just have to pick the number that fits the definition they're talking about and divide it by the total number of people. Now, if they say out of the females, no, let's say out of the males, pick never married. So now the total population we're actually looking at is much smaller. Total males is 123. Never married, who's a male, is 43. So the odds would be 43 out of 123. And so that would be our odds there, because we're not looking at the full population, we're looking at just the male population. So if I pick a a random male, what are the odds they've never been married? Now we're looking at slightly different values. But that is the first 4 sections in chapter 11, our introduction to probabilities and permutations and combinations, and that will allow us to better understand some of the numbers we see in the news or from people around, make sure that we understand what it is that's going on. If you've got questions, let me know.